So let's take a quick look at using all of this information to determine if a few things are true. Let's say we have a set, any set, S. Do the following hold without telling you what the predicates are? For all x in S, P of x or not P of x. Well, this is just stating that if we look at any element in S, either the predicate holds or it doesn't. And while a predicate on its own does not have a truth value, anytime we look at, say, if we have an element A in our set S, P of A is going to be a proposition that is either true or false. So either P of A is true, or if it's false, not P of A will be true. And so this holds. On the other hand, if we look at the second proposition, we see that for all x in S, P of x, or for all x in S, not P of x. Well, while the first one's saying for every element in S, either this property holds or it doesn't, the next one is saying every element meets this criteria or all of the elements do not meet this criteria. And that doesn't work. We can think of simple predicates that we've already seen. Like if we let our predicate P be the property that a number is even. Well, not all the numbers are even, so these would not work. Whereas a number that is either even or it's not even, they're not all even or not all not even. So consider this proposition for a non-empty set S. So we have some non-empty set. Can we show that if everybody's doing it for all x in S, P of x implies that at least somebody is? Well, we can in this scenario because we said this is a non-empty set. So if we assume the antecedent, which means we assume the piece coming before the implication, then can we show that the consequent is true? Well, we're assuming that we have this non-empty set S, and we say that for all x in S, P of x is true. So we know that we have some element A in S, and we're going to assume that P of A is true. But that's all I need to show that there is one, at least one. This wouldn't work if this was possibly an empty set, but this is a non-empty set, and so we know we have at least one. So if everybody's doing it, somebody is. What about this? And this can be an interesting one to ponder. All even prime numbers greater than 13 have 7 as their last digit. Is that true? This might seem crazy for multiple reasons. There are no even primes greater than 2. Okay, well, this set is very small. And we say they have 7 as their last digit. Well, first of all, if a number ends in 7, it's not even. So we have all sorts of problems. But is this true? The answer is, it is. And this is because if we consider the set of all even prime numbers greater than 13, that set is empty. And so all of them have 7 as their last digit. All of them have 3 as their last digit. All of them have 5 as their last digit. All 0 of them, you can say anything you want, and it's vacuously true. There are none of them. So the claim, we can't disprove it. The claim holds. What we call this is vacuous quantification. So this is quantifying over the empty set. And what that means is for all x in the empty set, P of x is true. This is a proposition is said to be vacuously true. It is true for every element. There just happen to be none.